Assalamualaikum warahmatullahi wabarakatuh and a very good morning to the respected panel and fellow friends. My name is Natalia Ain binti Onjasmi and today I'll be presenting my final year project entitled Converting Sulfonated Rice Husk Waste into Activated Hydrochar for Cationic Dye Removal under the supervision of Associate Professor Madya Chemist Dr. Raja Razwan Rajajaris and my co-supervisor Associate Professor Dr. Ali Jawad. To begin with, I would like to introduce the background of this study. Rice husk is an abundant agriculture byproduct generated from rice milling. It is rich in cellulose, hemicellulose, and lignin, making it suitable precursor for carbon-based material. Utilization of rice husk not only adds value to waste but also helps to reduce our environmental pollution. Based on this background, several key problems can be identified. First is industrial dye effluents are toxic, non-biodegradable and persistent in aquatic environment. At the same time, rice husk remains underutilized despite its high carbon potential. Therefore, there is a need for low-cost, sustainable and efficient for dye removal. So, the objective of this study are threefold. First, to convert sulfonated rice husk into activated hydrochar using hydrothermal assisted sulfonation by sulfuric acid. Second, to evaluate its absorption capability for methylene blue removal. And third is to examine the efficiency of operating parameters on the absorption performance. Next, I will briefly explain the methodology of this study. Rice husk was first washed before undergo drying process at oven at a condition 100 degrees Celsius for 24 hours. Then dried rice husk was ground into powder and added concentrated sulfuric acid before placed in hydrothermal container for activated hydrochar process at a condition 100 degrees Celsius at 14 hours. After the reaction, the product was washed until neutral pH, dried, sieved and stored for future purpose. Characterization was carried out using FTIR, PSEM-EDX, and pH-BZC analysis, while optimization process was conducted using box backend design, focusing on absorbent, dose, pH, and contact time.
The literature review covers key areas including water pollution, agriculture waste, dye classification, and the absorption process. It also includes hydrothermal carbonization, box bank design, and response surface methodology optimization as the foundation of the study.
Continue with results and discussion. As you can see, FTIR spectra confirms the presence of functional groups such as hydroxyl and carbonyl groups at raw rice husk. After sulfonation, sulfonic acid group are observed, confirming successful chemical modification. After the absorption, it shows a band shifting and changes in peak intensity, which indicates that methylene blue dye have interacted with the absorbent surface through electrostatic attraction and hydrogen bonding. Morphological and elemental analysis are performed using PSEM-EDX. At raw rice husk, it shows heterogeneous structure and distribution of big pores. Meanwhile, at sulfonated rice husk, it exhibits bigger pores, fissures, and indentation, so validating the impact of carbonization of H2SO4, which improved the mesoporous structure. After the absorption, denoted there is a decrease in porosity and development of dense surface, which indicate that the dye was effectively absorbed. To optimize the absorption process, box Benken design are applied, where the highest methylene blue removal efficiently is 95.9% achieved at an absorbent dose of 0.06 gram, at pH 10 and contact time is at 17.5 minutes. This confirms that the prepared sulfonated hydrochar has a strong absorption capability. Moving on, the surface change behavior was analyzed using pH-BZC. The pH-BZC value of the absorbent is approximately at 5.1. Consequently, when the solution's pH exceeds the pH-BZC, the surface becomes negatively charged, enhancing electrostatic attraction toward the cationic methylene blue. Meanwhile, for statistical evaluation using ANOVA shows that the Potts-Penkin model is statistically significant with a high F value and a p-value that is less than 0.0001 that shows that the model is reliable for predicting methylene blue removal. Model adequacy was further evaluated using residual and predicted plots. The residual plots are approximately normal distributed and closely follow the reference line. Meanwhile, a strong linear relationship between the predicted and expected value confirms the suitability of the model.
The dye removal performance was influenced not by a single factor, but by the interaction between pH, absorbent dosage, contact time, and initial dye concentration. The interaction between pH and absorbent dosage show that at acidic pH, the absorbent surface become more positively charged with strengthened electrostatic attraction with the dye. When combined with the higher dosage, more active sites were available, leading to higher removal efficiency. The interaction between contact time and initial concentration show that lower dye concentrations reach equilibrium faster, while higher concentrations require longer time for dye molecules to diffuse into the pores. In addition, the combination of acidic pH and sufficient contact time allow both electrostatic attraction and pore diffusion to occur effectively. This proves that absorption performance depends on the synergistic effect of parameters.
To conclude, rice husk was successfully converted into sulfonated hydrochar via the hydrothermal-assisted sulfonation. The prepared sulfonated hydrochar demonstrated excellent absorption capability for methylene blue dye removal by achieving a maximum removal efficiency of 95.9% under optimal conditions. The influence of key operating parameters including absorbent dose, solution pH, and contact time was successfully evaluated and optimized using Potts-Penkin design.
For future work, different activation methods such as chemical activation using suitable activating agents can be explored to further increase the surface area, pore development and absorption capacity of the hydrochar. This absorbent can also be tested for the removal of other types of dyes and heavy metals to evaluate its versatility and effectiveness in treating different kinds of wastewater pollutants. In addition, more detailed absorption, isotope, and kinetic studies are recommended to provide a deeper understanding of the absorption mechanism and rate controlling steps involved in the process. Finally, a continuous flow or column study should be carried out to stimulate real wastewater treatment conditions and assess the practical applicability of the absorbent on a larger scale.
So these are all my reference, and with that, I conclude my presentation. Thank you, and I welcome any questions from the panel.